Many companies, banks or internet companies or telecoms, have a lot of data on clients' events, and embeddings would be very convenient to represent these data. These are vectors of fixed length. The senior research fellow of AIRI and managing director of Sber will tell you about contrastive learning for event sequences. Hello, my name is Dmitrii. I work at Sberbank at the AI lab and at the AI Research Institute. I'll tell you about the sequence embeddings that I think have been the game changers for data science in banks. I'll tell you about callers that we offered early in 2020. But let us talk about what embeddings are. The sequences. Embeddings are fixed length vectors that contain as much information from the original sequence as possible. Probably all the information, ideally. You can have different means and ways of doing embeddings, but what we need is to have no labeling, external labeling. One of the main advantages is that we automate the design of parameters or features, and each client may have many transactions, and submitting that to a machine learning model would be a difficult thing to do, but data scientists would come up with aggregate features or traits, trying to calculate the proportion of this or that category in your spending. With embeddings we can do that automatically. The second good advantage is that they are smaller than our sequences, and that helps us save computing power, and definitely this is good for the ESG goals, and it's easier to process and store these data. And the third, embeddings helps us protect data, because the original initial sequence cannot be restored from an embedding. So inside the ecosystem of ours, we may spread them far and wide, not fear that someone will receive access to the client's transactions. Let's now have a look how we can receive these embeddings from sequences. The contrastive machine learning is one of the notions that we use. It's like identifying and recognizing an individual by photo. If we have several photos of a person, we say that these photos belong to one and the same person, and the scheme would kinda work as follows. The encode and neural network learned to produce such embeddings of photo where the photos of the same person would be next to each other in the embedding space, and different people's photos would be far away from each other. And this is described by the loss function. It's very simple. The first part of the function, the first component, is responsible for penalizing the network for not putting next to each other the embeddings of the same entity. And what shall we do when we have the sequence of client data, like the transactions? And that can be not only about transactions, but about any data that make a sequence. It is noteworthy that we'll only have one sequence per client, and we don't have options of this sequence, several options of this sequence. And we thought, why not try to break it down into subsequences, and those subsequences would be the sequence, as if the sequences of the same client belonging to him or her. And later it all boils down to our marking goal. You can draw a parallel with augmentation. We may build several augmentations of our original sequence. And Hinton came up with a similar notion. CLR was the title of his paper, and with respect to Hinton's case, it was like in his paper it was for the pictures, for the images. How can we break the sequences into subsequences? We can select randomly some of the events out of the sequence and say this is a new sequence, or we may take a continuous segment of a sequence and say that it constitutes a new sequence, or like if we need several segments, we should see to it that they don't intersect. And the most appropriate means, as we argue, is to take an uninterrupted, a continuous segment of a sequence, because in this case would be in the same domain as the original sequence distribution, and that would be important and give us better experimental and trial results. The overall schematic looks like this. We have sequences, input sequences. We break them down into several subsequences and submit it to the encoder that can convert them into embeddings, and then we would calculate our loss function, and we would train the neural network. Hence, now let's talk about what we can do as our events are kind of construct comprising several fields. Like if you buy with a card, pay with a card, those fields would include the currency code, the country code, like categories, and numerical values, also the amount, the date. But we want to have the uniformity of all that, homogeneity of all that, with a small vector that would code a transaction of similar. All the vectors should be of similar scale, and we would teach the embedding tables, would train the embedding tables, and for each of the continuous variables, uninterrupted variables, we would train the batch norm layer. And then all the variables would represent a transaction, one transaction. Then we may use GRU or a transformer network. Both have their own pros and cons. And by and large, this design is trained in parallel, like in the end-to-end mode. And let me tell you quickly how we can apply these embeddings. Like if we have trained the coder and it produces small-scale embeddings, well, at the outset, for each of the clients, we would calculate an embedding and add it as a feature for a client, as a trait, and we would train like any machine learning model like gradient boosting. So our embedding would give another set of parameters describing the sequence of events. And it is more efficient, but more sophisticated also, and more complex. Towards this CT encoder, we would add another layer that would resolve the final task, like of classification, for example, and teach and train them with metrics of like credit scoring. And this part in charge of the contrastive learning is kind of the pre-training of the body of our network. That works okay with a little marking, like in green color at the graph. You can see the green color is for the pre-training and the red is for this training from scratch. Along the x-axis will show the sample of the training, the size of a training sample, and the more the difference, the more well the graphic representation deviates. Let us have a look at how our embeddings are represented. It is a 2D representation. GSNF. These are embeddings for card transactions and payments. In color, you can see the monthly amounts, and it is obvious here that in green or red color, the clients are clustered. We can see that the embeddings are placed in certain positions and clustered, not randomly, but following a pattern. And these are checks, bills embeddings, and the color represents age groups. In violet color, there is a special clustering zone in the upper part of the field. Like in the green and the blue are either above it or below it. So the collocation, the placing of embeddings is not random, is not. Well, it has a lot of information about the initial sequence. So on the right-hand side, the churn actual data are shown. You can see that in blue color, there are a lot of clients that left us in the upper part, and there are no green clients that stay with us, whom we retain. We have been applying that approach in our bank for a host of goals, of tasks, and we have tried to look at embeddings, and there are two types of embeddings. These are embeddings for card transactions and for money transfers between legal entities. And with many tasks we have a considerable, crucial increase.
Так происходит потому, что последовательность платежей юрлиц она сложнее, чем последовательность платежей, последовательность покупок по карте. С картами все в принципе довольно просто. Там понятно, как
it is clear how to build a sequence for cards, but with respect to payments between legal entities, the aggregate parameters are hard to build and represent because the legal entities have a sophisticated hierarchy. And, well, they are more sophisticated structures. And here we don't think what features are typical of legal entities. We just build embeddings and train the model. And that definitely rids us of the headache. Well, that brings me to the end. Suddenly, we have a lot of details, and you can read our articles. There is a link. And another important point to make is that now I told you about our method, citing the transactions examples. And we experimented with gaming sequences in online games, or bills, sequences, and purchases. So it is not only about bank transactions. It may be applied to anything, like to visiting websites. It may have many an application it may have. It is a universal feature. I would be glad to take your questions. Thank you. Dima, thank you very much for a very interesting presentation. Among the questions, there are compliments. They say, well done, good job. It has been an interesting presentation. Thank you. I'm pleased also.
The question, which is a bit wider, what you've been talking about. So what are other ways to create the embedding of sequences, and which advantages and disadvantages they have? You said that you've tested the current methods on different types of datasets. Can you elaborate on that and how you can find typical patterns for different data? It would be interesting to talk about that in detail, but we compare 4 different methods, and there is a lot of information. CPC, Contrastive Predictive Coding method, which is a bit different from our one, so it works in the following way. We are trying to forecast the embedding of the next event in the sequence rather than following the sequence. This method is quite efficient when we need to have a dynamic embedding, when we need to perceive the information in a fast manner, the fresh information with sequence, if we need different types of information. So our method is more efficient on the data sets we were able to receive. Our method is better than CPC. Because the sequences can be reiterated, like transaction on cards. But there might be different situations with different efficient methods. But that might be your next test. Yep, that might be the case. Thank you very much for your presentation. The audience really loved not the content itself, but how you deliver your presentation. Thank you very much.